Hello everyone and welcome to the Callum Cymru revision sessions. The session this evening will focus on physics at A2 level and will be presented by Mr James Ridd from Cynvig Comprehensive School in Bridgend. The session will last 45 minutes where James will revise Vibrations 2.5. If you have any questions during the session, please use the Q&A section and we'll do our best to answer your questions. You will see that there's a hyperlink in the Q&A section. Please leave your name and email, and if you are interested to receive more information on future events. Today's session will be recorded, and the recording and any relevant resources will be uploaded to the e-sgol website under the Callum Cymru tab. Thank you, James, and over to you.
Thank you, Jane. Yes, so vibrations then, following on really from a previous video made about circular motion. I'd advise maybe looking at that if you're looking at this in its recorded state to offer you a small introduction to this topic. Now, it's called vibrations, but really it's probably more commonly known as simple harmonic motion. Some examples of simple harmonic motion then just to kick off with. For example, when we think about vibrations and simple harmonic motion, things to consider would be maybe the bobbing of a float on at the end of a fishing rod. Perhaps a swing, for example, is another good example of simple harmonic motion. We've also got a pendulum on a grandfather clock, a mass on the end of a spring. Maybe some more less intuitive ones, but the way a drum skin would vibrate after it has been hit in that time that it's oscillating would be an example of simple harmonic motion. And then it naturally follows that a guitar string does the same kind of thing. And then the example I got up the top here, the shock absorber on a car. Well, if you think about a mass on a spring, as I've got down in the bottom corner here, you can see obviously there's just a practical example would be a mass on a spring in terms of a car. A car would be a mass on the end of a spring, and obviously shock absorbers used to make the ride a lot smoother. In the middle here, I couldn't resist putting in another pendulum, a very famous pendulum known as Foucault's pendulum. And if you get the opportunity to Google that and look it up and maybe find a video on it, I recommend you do so. It's a very interesting and elegant experiment that shows the fact that the Earth is indeed rotating. Of course, if you believe that the Earth is round, some people don't these days. Anyway, moving on. So the content, what do we need to cover today? It's all here. It's quite a big one, this, so I'm not going to waste any time and I'm going to dive straight in. So to begin with then, we're going to look at the definition of simple harmonic motion as a statement in words. Now, I took the liberty of actually typing this out earlier on because no one really wants to see my handwriting. SHM then, a simple harmonic motion, occurs when the acceleration of an object is proportional to its displacement from the equilibrium position and is in the opposite direction. So let's just sort of pick that apart and think about what it means. Here, if you look at this this green pendulum here, if you imagine we set that into motion, then at some point later on, of course, it would be in this orientation, and it would also pass through the equilibrium position. Okay, 0. This is X. When the pendulum is in fact at this point here, we can observe that at that moment it would be stationary and that it would in fact have a maximum displacement which would be equal to the amplitude of oscillation. In this case, it would be minus A. It would oscillate between minus A and plus A. In this state of maximum displacement at the amplitude, it would also have its greatest acceleration. That is sometimes a little counterintuitive because at that moment in time, if you imagine a pendulum coming to the end of its swing, it would for a moment be stationary, and it wouldn't necessarily be at all obvious that in that state it is undergoing a maximum amount of acceleration. But we have to accept that something can be accelerating yet stationary for a moment in time. A really simple example of this would be throwing a ball in the air. As you throw the ball in the air, you know that that ball is accelerating downwards with acceleration due to gravity of 9.81 meters per second squared. It's accelerating downwards, which is causing it to decelerate as it reaches the maximum height of the throw. And therefore, instant in time is obviously stationary, and it continues to accelerate downwards thereafter. Now, of course, therefore, we are proving that something can be accelerating. The acceleration doesn't disappear momentarily. It is accelerating yet stationary for an instant in time. And this is what we've got here. So here we have maximum displacement and therefore maximum acceleration. And the direction of the acceleration is back towards that equilibrium position. Okay, so this object is going to accelerate back towards that equilibrium position. When then, of course, we're in this other orientation here, the acceleration again is back towards that equilibrium position, back towards a fixed point, as it's sometimes referred to. The only time, in fact, where the pendulum is not accelerating is when we're in the center here. Now, at this point in the center, because we are at zero displacement, we also have zero acceleration. And again, just referring back to the definition, SHM occurs when the acceleration of an object is proportional to its displacement. So in this case, if there is no displacement, then there is no acceleration. And therefore, it is just moving through that point. And it's a point actually where there's no acceleration. It's also the point where it's moving at maximum velocity as well, which is something we'll come to a bit later on. So there's a definition then for simple harmonic motion and a statement in words. Next then, we're going to cover this, that A is equal to minus omega squared x as a mathematical defining equation of simple harmonic motion. Right, this is an important one and a big one. We're actually going to kill two birds with one stone here. Now, to define and sort of come up with that expression, we're going to do a little bit of maths because I think it's important to understand where that expression comes from. To begin with, then, I'm going to imagine an object which is moving in a circular path. Now, objects moving in circular paths also will exhibit simple harmonic motion in one direction. So what I want you to imagine is, as this object goes around in a circle, if I just imagine its motion in the x direction at the bottom here, what I'd observe is from its initial position, starting off at a maximum positive displacement, it would go to zero displacement after a quarter of a cycle, and then onto its maximum negative displacement 180 degrees or half a cycle later. So if we are just looking, if you like, we'll draw a little eye here, why not? If we are just looking at the motion of this object in one dimension, i.e. the x direction, then it will display and exhibit simple harmonic motion. And there's some lovely experiments you can do to demonstrate that as well. So let's imagine then the position of this object maybe sometime later. And let's imagine what its projection would be in that x direction. Now, it has a radius here, because we were talking about a circular path. We've got a radius here, and we've got an angle or angular displacement of theta. And what we are concerned with really here is this distance here, this distance x. What is this displacement going to be, and how is it going to change with time? Because we're going to derive one of the many equations that you need for this topic, and we're going to do that right now. So if we wanted an expression for x, I can just look at that. I can just look at that triangle there, okay? And I hope you can all see that triangle. And I can come up with an expression for x and say that x is equal to r cos theta. All right, r cos theta. Now, We can make this a bit better because the thing about R here is that when you consider this initial position here, R would be equal to A, the amplitude, the maximum amplitude. So in fact, we're going to say that, well, let's set R equal A, and then we'll rewrite this as X is equal to A cos theta. And that way then, like if you consider the initial condition here where theta would be equal to 0, X, the displacement, would be equal to A, because the cos of 0 degrees, of course, is in fact 1. So X in that scenario would equal A. Right, good stuff. Now we're going to think about this theta bit. Now theta from the last topic, this is angular displacement. You know, it's what you commonly just call an angle, and we know that. But to give it this proper terminology would be to call it angular displacement. Now, just like regular displacement, to calculate that, we would need to know the velocity and the time. To calculate angular displacement, we need to know the angular velocity, and we need to multiply that by the time. So what we're going to do is substitute that in there, and we end up with X is equal to A cos omega t. And that is one of our first expressions. We're going to go one step further here as well. We're going to add in something called the phase constant. Now, when you look in your textbooks, you will see an iteration of this with a phase constant involved as well. I'll talk about the phase constant a little bit more later on, but really all you need to know is that the phase constant is an angle which you can add into this expression, which will in fact hang on, so I put my bracket in the wrong place there, I do apologize. Just a second. A cos omega t plus, yeah, it's an angle which you can use to orient the equation or make the equation fit your initial conditions. So a question might say to you, when t equals 0, x is equal to 0, and you go, okay, when t equals 0, x equals to 0, and I must apply a phase constant to this equation such that it will produce that outcome for me. Another question, though, could be really awkward and say something to the effect of, when t, time is equal to 0, x is equal to a. And then you need to go, right, okay, I need to now apply a phase constant in here to allow for that outcome for the initial conditions. And hopefully we'll have a chance to look at that a bit later on. Anyway, what I'm going to do now is going to take this equation for x. Whoopsie daisy. Let me just turn something off a second. There we go. Into shape. We're going to take this expression for x, and we are going to differentiate it. Now, for those of you in maths, you'll recognize this, okay? The rate of change of x with respect to t is what the velocity is, and we'll derive an equation for velocity here now. If you do that with the cos function, those of you who do maths will know that cos becomes minus sine, and the differential of the bracket comes out. So in this case, then we end up with minus a omega cos, oops, no, sine, sorry. Oop. A omega sine omega t. And this is our next expression. So we've got two now. We've got one for x, and now we've got another one for v. And we're going to go one step further and just say, well, acceleration is the rate of change of velocity, or dv by dt. And if we differentiate this equation one step further, we take the differential out again, and we end up with minus a. Now omega comes out again, so we end up with omega squared cos omega t. All right, minus, yeah. So when you look at this equation, what you'll notice is that it's perfectly fine and valid on its own. And in fact, we'll highlight that one. But I'm just going to further highlight some key parts here, because up here we've got A cos omega t, and down here, look, we've got A cos omega t. So we can now apply a substitution here, and we will do that to derive that equation that was mentioned in the specification just now. So A is equal to minus omega squared x. We've substituted x in, and then that, everyone, is where that equation comes from. And the equation is telling us what we already know, or what we've already said about SHM, that it occurs when the acceleration of an object is proportional to the displacement, the equilibrium position, and it must be in the opposite direction. So if you look here, A is indeed proportional to x. A is indeed proportional to x, and this minus sign here in the middle, that tells us that if x is negative, A will be positive and vice versa. So it handles that second part of the statement about the direction as well as the magnitude. Okay, so Mr. Reid is going to just say that, yeah, we've done that last part. Now we're going to look at the graphical representation of the variation of acceleration with displacement during simple harmonic motion. So we're going to look at the graphical representation of what we just talked about, but we've also done this as well. We've done D. Well done, us. Right. So graphically then, what does this look like? Well, we know what a directly proportional relationship is, and I'm going to go mad here. I'm going to use my ruler. Look at this. Crazy. Okay. Now, if it was just regular in terms of its proportionality, you know, if it was a positive relationship, then it would be in that direction. But because of that minus sign, when A is positive, X is negative, and when X is negative, sorry, when A is positive, X is negative. When X is positive, A is negative. So that means that we'd have to draw our line like so. All right, through the origin. Now, I don't think there's any easy way of getting rid of my ruler. I have to go back up here, like so. All right, and yeah, that pretty much covers it. All right, it's not a particularly hard graph to draw. In some questions, they might ask you to put some numbers in mind. So, for example, if you knew the amplitude, then you could, in your sketch, mark that value on. If you knew what the amplitude was, that would be A. All right, and similarly, if you knew the maximum acceleration, you could mark that on too. All right, that would be A max. That's a quick one, wasn't it? Next then, the terms frequency, period, amplitude, and phase. Now, really, I don't think that there's much to talk about here that we haven't already covered. The terms mean very much the same thing. So the term frequency is the number of cycles or oscillations per second, as you've come across previously in waves and, of course, on circular motion. Period, the time for one complete cycle, or if you like in this instance, maybe the time for the pendulum to go back and forth, or the time for the spring or the mass on the end of the spring to go up and down and complete one complete cycle. Amplitude we've already discussed, and phase. Now, phase applies in the same way as it did previously. So if I'm talking about a cycle, one cycle or one complete cycle is 360 degrees or 2 pi. And if I'm talking about half a cycle, I'm talking about 180 degrees or pi. And if I'm talking about 90 degrees, I'm talking about pi by 2. And of course, everything else in between. All right, so we'll just encounter that and deal with it just like we've done before when we're talking about phases and if you like, proportions of cycles. We will very often discuss that in terms of pi. F then, period as 1 over f, or 2 pi over omega. Now, again, I don't think I did an F for this, did I? No, because it's a real easy one. So previously, you will have come across the fact that omega is equal to 2 pi F, and we know that F is equal to 1 over T, and because F is equal to 1 over T, then actually you can do a substitution quite easily, look, and get this relationship out. All right, so we'll leave that at that, okay? G then. V is equal to A or minus A omega sine omega t for the velocity during simple harmonic motion. Now, this has already been defined up here, look, okay? We've already done that as well, so we'll give that a big tick. What I will say, though, is a handy little equation to remember here, and that is, that is V max. Handy little equation to remember, because V max is, as it suggests, the maximum velocity. And the maximum velocity will happen when this part of the equation here, when this part of the equation returns a maximum value. What's the maximum value that the sine function can return? Well, it's when that equals 1. So, for example, were omega t in this particular iteration were to equal 1, or 90 degrees, sorry, then the sine of 90 degrees is 1, and therefore V would be its maximum value. So what you can assume to work out what V max is, you can just assume that sine omega t is equal to 1, and therefore V max, as a nice little expression, is equal to, I did try and go for a black pen then, but there we are, is equal to minus A omega. So it's another little handy equation to remember. Next then, the graphical representation of the changes in displacement and velocity with time during simple harmonic motion. Okay, this takes a bit of drawing, this does. So we've got to look at the graphical representation of the changes in displacement and velocity during simple harmonic motion. So in fact, we're going to do all three. We're going to do displacement, velocity, and acceleration at the same time. So let's imagine our, in this case, situation where we've got t. So this is t equals 0 here now, right? Imagine this is 0. This is beginning its oscillation, whatever it might be. Could be, you know, like we've mentioned before, it could be the bob at the end, the float at the end of the fishing rod. It could be the child on the end of the swing. Whatever we are considering here, moving with simple harmonic motion, it starts its journey with a maximum positive displacement, and then it's left to accelerate towards the equilibrium position. Now, crucially, if you consider the instantaneous velocity at any one given moment in time, that would be given by the gradient of that line. You'll notice that the gradient here is negative, which absolutely makes sense, because if we were to release this object from its maximum positive displacement, it would indeed be accelerating towards the equilibrium position, but it would also be moving with a negative velocity. So that makes perfect sense. And in fact, we can see that negative velocity in the graph below, because just below here, look, we have a situation where we start off at maximum displacement, where we'd expect the velocity to indeed equal 0. And then very shortly after, its velocity starts to increase and gets larger and negative at the same time. So if you look here, we can represent that with this pendulum. So this is t equals 0. And initially, we're going to have a tiny little velocity v here. It's going to be negative. 1/4 of a cycle later, look, we're going to get minus V max. Okay, and that happens when x is equal to 0. All right. This would also be A is equal to 0, incidentally, as well. And then I should maybe label this. This is x is equal to A, or if you like, the maximum positive displacement. Here we've got x is equal to minus A. Now, at this very instant in time, it would be stationary, okay? Just about to move back towards the center, so V would equal 0. And then finally over here again, V would equal 0 again. So we've kind of labeled on here now the displacement and the velocity. And we should also label the acceleration as well. Now, as previously mentioned, because we've got maximum displacement, A here would be equal to a maximum value, okay? So A would equal, if you like, some kind of maximum. And then over here, A would equal some kind of negative maximum, all right, because it's heading back towards the center. And really, this is the graphical representation of all that then. So as the displacement, as it swings back towards the center from its initial positive displacement, when it gets to the center, it will have a maximum negative velocity, and it will also have 0 acceleration. Then, as it maybe goes 1/4 of a cycle later, and it ends up with a maximum negative displacement, which is over here now, okay, maximum negative displacement. Then, of course, we now have 0 velocity, which is here, 0 velocity, and a maximum positive acceleration. So these 3 graphs, as we go through the cycle, have a certain relationship. There is a 90-degree phase lag here. So if you like, the displacement and the velocity are out by pi/2. And then between the displacement and the acceleration, you'll notice these are out by a factor of pi, or the phase relationship with those graphs is out by a factor of pi. In other words, between the displacement and the acceleration, they're exactly out of phase in terms of where the peaks and the troughs are. Whereas with the displacement and the velocity, it is a factor of 90 degrees. So yeah, at any one given moment in time, you're going to need to maybe describe any one of those 3 quantities: displacement, velocity or acceleration, and the relationship between them. I hope that's a little bit clearer now. Next, the equation T is equal to 2 pi root m over k for a system having a stiffness, force per unit extension K, and mass m. And the equation of T is equal to 2 pi root L over G for the period of a simple pendulum. All right, let's take these 2 on board then, right? Mass, spring, it does its thing. It oscillates up and down. Sounded like I was going to break into song end, didn't it? But no, you don't want to hear that. Anyway, very simply speaking, the time period here, without going into too much detail, because you can labor over this a little and derive the equation, we're not going to do that, is equal to 2 pi root m over k. There's not much more to say other than t is proportional to root m, and that still means that as m gets larger, the time period gets larger. Does that make sense? Well, yes, it does. If you imagine a heavier mass on a spring, it oscillates more slowly, and then it's inversely proportional to k, which implies that the stiffer the spring is, i.e. the higher the value of the spring constant is, the stiffer the spring is, then the shorter the time period would be. If you like, the oscillations would be quicker. Again, makes sense, doesn't it? Your intuition tells you that that's probably right. So anyway, handy little relationship there. When we come to think about a pendulum then, so that's a mass and a spring. I've drawn enough pendulums. I'm not going to draw another one. No, I'm not going to do it. You get the gist. They're all over this. So you've seen enough. The time period here is equal to 2 pi root L over G. Again, proportional to T is proportional to the root of the length and inversely proportional to the root of the gravitational field strength. So gravity pops in there, and in fact you can use this, and you'll have probably done this in the specified practical work that you've already completed. You'll have used this relationship and the motion of a simple pendulum to determine a value for G, the acceleration due to gravity. And it's worth probably stating that were you to take exactly the same pendulum to the moon, obviously with its lower gravitational field strength, you'd expect a longer time period. I'm not going to label that point any further. We're just going to call that done. All right. So the graphical representation of the interchange between kinetic and potential energy during undamped simple harmonic motion. Perform simple calculations on energy changes. Right. Okay. So energy then. If we take a look at this little relationship here, then at a maximum, let's start here. Okay, at a maximum negative displacement, this would be. What we'd expect then is no velocity, and we mentioned this earlier on. We said that at maximum displacement for a moment in time, this object is stationary. Therefore, it stands to reason that it will have no kinetic energy. And you can see the kinetic energy curve here in the situation we're talking about. There is no kinetic energy at maximum negative displacement. Then, as it accelerates towards the equilibrium position, we already established previously the Vmax, or the fastest velocity happens and occurs as we move through the equilibrium position. So we would expect at this point to have the maximum kinetic energy. And then finally, as it reaches maximum positive displacement, or the amplitude, again, it comes to a stop, and we find that the kinetic energy is again 0. Now, this is an example of energy transfer, the conservation principle of energy. Energy cannot be created or destroyed, merely transferred from one form into another, and therefore that kinetic energy is transferred into and out of gravitational potential energy. Now, when the pendulum is in this orientation here, it has essentially a small amount of height through which it falls, in a sense. It goes from that larger that larger height then to the smaller height at the equilibrium position, and therefore the gravitational potential energy here is equal to mgh, or delta h as I did it, delta h. So at maximum displacement, we have maximum potential energy, which is this dotted line here, okay? And as we go through the equilibrium position, essentially, that's where it loses all of its gravitational potential energy, or if like the change in gravitational potential energy is completed, and we have no GPE there. Point worth noting, though, that the total amount of energy, i.e. the gravitational potential energy plus the kinetic energy, always remains constant. So you can expect, if you like, to maybe have, you could write a statement, couldn't you? You could say a half mv squared plus mgh equals constant here. And this is for an undamped system. This is assuming now that no energy is being lost. More on that in a little bit. Okay, we are cooking on gas. for now. Although I hear that a lot of new schools aren't even having gas anymore as an environmental consideration. Remarkable. Free oscillations and the effect of damping in real systems. Right, what's a free oscillation then? Well, if you let something that does oscillate do so freely, we consider that a free oscillation. A child, if you will freely oscillate on a swing. I mean, let's just assume for a second they're not doing that, you know, that thing that propels you on the swing. I don't know what you'd call that. You know, that thing where you're not pushed, but you're causing yourself to gain momentum on a swing. What's the word for that? Anyway, doesn't matter. If you imagine that we have pushed said child and now they are freely oscillating, they will do so at a certain, if you like, natural frequency, we'd call it, right? A certain natural frequency. Now, the effect of damping then, well, you know, you're all very young, so you won't really appreciate the hard work that maybe a lot of your parents put into swinging you as a young child on swings. And I can tell you now, having been through this, that some swings are better than others, and not all swings are created equally, and some of them are rusty and they're slow, and there's a lot of friction, and such a swing would be an example of a damped system. For if you are to push a child on a swing and let them freely oscillate, and I would frequently say that to my children, are you enjoying your free oscillations? If you let them free, if they came to a stop relatively quickly because of the amount of friction, because we lose a lot of energy from the system, we'd say that was a lightly damped system, right? And then the more damping you add, the quicker that energy is dissipated, and the quicker those oscillations will come to an end. All right. So if we have a look at damped systems here, are we onto that yet? Yeah. Okay. Free oscillations and the effect of damping on real systems. So practical examples then of damped oscillations. Where are we by? Yeah. Would be to think about what damping, let's think about what light damping looks like first. So if you imagine the child on the swing in the example I just gave, and when we remember we were talking about a bad swing here, maybe, okay, that had a light amount of damping, then what we'd expect is that the amplitude would decrease with time. And you can see there's a little envelope sort of drawn here, okay, to show how that amplitude goes down. Now, we can, though, of course, it's worth mentioning as well that even though the amplitude decreases, the time period here will remain the same. Okay, so we'd expect t to remain constant. What about more heavily damped systems? Well, a heavily damped system then would have perhaps its oscillations decreasing a lot quicker, like so, right? So you could have a heavily damped system that might look a little bit like that. Now, it depends on the scenario that we're looking at, but very often it's not desirable to have too many oscillations in certain things. So, for example, if you were designing a car and the engine is obviously rotating, it was going to cause some vibrations. You wouldn't want those vibrations to propagate throughout the vehicle. You would want to stop those vibrations as quickly as possible. So you might critically damp, or maybe even damp some more. You heavily damp some more, so you'd reduce the amplitude of those oscillations very, very quickly. And then you might even, in some systems, apply what we call critical damping. Now, critical damping is where you don't even allow the oscillations to happen as such. You have a situation where you don't want it to let me get this right. You don't want it to stop oscillating the shortest amount of time. You want it to be gradual, and you want to prevent the oscillations altogether. Such an example would be maybe a door closer. So in your schools, you have doors which won't just slam shut. They've got automatic door closers on them, that little thing at the top, which pulls the door shut. But when it comes down to that last bit, you don't want it to slam shut as quickly as possible because of people's fingers and such. So what you have is that, if you like, critically damp system that stops that from going any further or any quicker. Okay, so that's damping, and the 3 different types. Now, you'll notice here it's mentioned as well the importance of critical damping. Critical damping in appropriate cases such as vehicle suspension. So in the case of a vehicle, you would have to reduce the oscillations as rapidly as possible. It wouldn't be any good if a car went over a road, or a bump, sorry, in a road, and then continue to oscillate for some period of time thereafter. So you want to reduce and stop that vibration as quickly as possible, and you apply a lot of damping to do that. Forced oscillations and resonance, and describe practical examples. So forced oscillations then and resonance is where you cause something. There's some external driving factor that is causing something to vibrate. Now, such a good example of this would be, in fact, the child on the swing, because as you know, there is often an adult, usually a parent, pushing the child on the swing. And a forced oscillation is where the driving force, in this case, the push from the adult, is at exactly the same frequency as the natural frequency of the child on the swing. It would be no good if the driving force, i.e. the rate at which the adult pushed, wasn't synchronized with the oscillations of the child. So that is an example of a forced oscillation. Now, when the driving force, the frequency of the driving force, perfectly matches the natural frequency of the oscillator, then we say that resonance occurs. Now, a good example of resonance, well, I say it's a good example, a famous example, is the idea that an opera singer can, in fact, smash a wine glass. And there are videos of people who have done this on YouTube. Again, you can check it out. But essentially, the wine glass has a natural frequency at which it will oscillate. To determine that natural frequency, you could quite easily do so by giving it a little flick and it will produce a note. Now, if you, as a singer then, were to match that note perfectly, then you would be creating a driving force of the same frequency as the natural frequency of that wine glass, forcing it to oscillate. And if it does so dramatically, then it will, of course, smash. Okay. Now, this is represented by this resonance curve, where the natural frequency at the bottom here is represented by F0, and were it to be the case, okay, that, or we'll put amplitude on here, were it to be the case that a driving force matches that natural frequency, then we get, as you can see up here, maximum resonance. We get maximum displacement, maximum resonance. Now, if though we're either side of that, then of course you can see that we don't get quite as much of a, what we call maybe a frequency response or a resonance response. If we apply damping to this, and this is something we're going to just cover real quick, okay, if we apply damping to this, then in fact what happens is we end up with something like this, and maybe even something like this. Two things happen. The curve broadens. The natural frequency for maybe a lightly damped system, the natural frequency shifts towards the left, okay, so it goes to a lower frequency, and that will continue to do so, okay. The peak, the resonant frequency will, in fact, on the natural frequency, will go to lower wavelengths the more that we damp an oscillating system. Some examples of this then, just quickly, your eardrum. It's a bit gross, I know, but this is this oscillates, of course, and it does have a resonant frequency or a natural frequency oscillation. It has a couple actually, but around about 2000 hertz, it resonates very well. Okay, so if a sound wave which is around about 2000 hertz is incoming, then it will cause your eardrum to well, it'll match the natural frequency of the eardrum, or one of the natural frequencies of the eardrum, and cause it to resonate. This is why sounds which are 2000 hertz actually appear or you perceive as being louder, because it just so happens that your eardrum oscillates very well at that particular frequency. But for lower frequencies like 20 hertz or something like that, okay, you perceive it to be quieter. It's because the frequency response is not the same for your eardrum. Where don't you want this? Well, bridges. I've got a couple here. This is the famous Tacoma Narrows Bridge, which I'm sure you've all seen. The natural frequency of this bridge just happened to match the natural frequency of the wind as it sort of went through this valley, and it caused and set up this situation where, just like the child on the swing, it was giving it a gentle nudge at exactly the right frequency, and because it was giving it a gentle nudge at exactly the right frequency, we got this resonance and we got this very large amplitude of oscillation, which caused the whole thing to break. This also happened with the Millennium Bridge. Millennium Bridge is a bridge in London which experienced this lateral oscillation because the natural frequency of the lateral oscillation matched the frequency of people's footsteps, and it caused the whole thing to shake side to side. So the engineers and designers were thinking about the vertical but not the lateral, so they had to close that, and they had to damp it. They had to apply damping to it. And I can see that I've run over now, and I'm just going to finish this last bit off. Microwave is another one as well. So a microwave, the will have a frequency which matches the natural frequency at which water molecules oscillate. So the way a microwave cooks your food is by resonance. The natural frequency of the water molecules is matched by the microwave, and it causes that to start oscillating and warm up your food. And I think I'm going to just check these off. The variation of amplitude of force oscillation with driving frequency, and that increased damping broadens the resonance curve. We discussed that just now. Circumstances where resonance is useful. I didn't discuss circuit tuning, but maybe you can look that up. It's basically the idea that if you have an aerial, which is a receiver for a particular frequency, maybe it's a radio signal, then you want to design a circuit there which is going to resonate with the driving force, which in this case would be the frequency which you want to receive. So you want to set the receiver up to, if you like, resonate at the frequency which you intend on receiving. And then we talked about bridge design as well. So I do apologize for running over. I'm sorry we didn't get a chance to have a look at past paper question. Miss Owen, it's over to you now.
Okay, well, that's it now for our series of revision sessions. It's the end of the Physics A level for this term, and we'll be back in 2023 and 2024. And so look out for any details on the e-sgol website, and goodbye.